All right. I think that should be enough time for this question because we have 90% answers now. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses. Most of us selected option C. Okay. Carbon atom is bigger and has a lower ionization energy than oxygen atom. I mean, I think it makes sense too. So that's the correct answer as well. So why this is the case? In both cases, carbon and oxygen, the electrons are filled to the second shell. So here's the first shell already filled. Okay, and then in both cases, carbon and oxygen, you're filling electrons to the second shell as well. However, you have more protons in the nucleus of oxygen. As a result of that, these electrons are strongly attracted to the nucleus of oxygen. As a result of that, you're going to have a small electron cloud in oxygen. That's why oxygen atom is a smaller atom. And also, because they are strongly attracted to the nucleus, these are harder to be removed. Therefore, the ionization energy will be higher for oxygen as well. So those are the reasons. And then this can be explained via the shell model of the atom. All right. Any questions, concerns, comments at this point? Anything? Any concerns, comments at this point? Okay, so if that is the case, what we want to do now is, so we did explain the size trends using the shell model. We also predicted what's going to happen to the ionization energies. Let me show you the actual data as well for ionization energies. Okay, so we predicted the ionization energy is going to be higher when you go down, go across a period from left to right. Okay, and then here are the actual data. You can see that when you go from hydrogen to helium, the first period or first shell, okay, you can see the ionization energy increase. And then again, from helium to lithium, there's a big dip in the ionization energy. Reason is the third electron is filled to an outer shell, new shell, which is larger than the previous one. That is, therefore, the electron is away from the nucleus. Therefore, it's easier to remove it because there are weak attractions. And then across the period, from lithium to neon, again, the ionization energy increases. Why? Because you have more protons in the nuclei, the electrons are going to get more attracted to the nucleus. As a result of that, it's going to be harder and harder to remove the electrons. Okay, and therefore the ionization energy increases. Again, these trends continue, and these are called periodic trends. Okay, and we were able to nicely explain this using the shell model, so we don't have any issues with them. Okay, but however, we want to go a little bit further and try to see the ionization energies of all the electrons rather than just one or the first electron. All right, shall we do that? So that technique is called fourth electron spectroscopy. I don't want to do this. Okay, fourth electron spectroscopy. So in the fourth electron spectroscopy, we get the ionization energies of all the electrons rather than just one or the first electron. Okay, so I'm going to start with the first atom, okay, the hydrogen atom, which is the simplest form. Now, before I do that, I want you to pay attention to two things here in the fourth electron spectrum. The y-axis is the number of electrons, and the x-axis is the ionization energy. Now, here's the problem though. The ionization energy increases from right to left. Okay, we need to get used to it. Okay, you can see that the ionization energy increases in this direction. Okay, not the other way around. All right, I mean, that's the way the four electron spectra are presented to us, so we just want to get used to it. Okay, all right. Now, hydrogen. How many electrons does hydrogen have? How many? Only one electron. Therefore, how many peaks do you expect to see in the fourth electron spectrum? Yeah, just one. Here we go. Here's the fourth electron spectrum of hydrogen. All right. Helium. How would the helium fourth electron spectrum differ from that of hydrogen? Can you draw the fourth electron spectrum of helium on your whiteboards? Go ahead. I'll give you a minute. I think everybody has a whiteboard thanks to our TAs, wonderful TAs. Okay. So if you can draw the fourth electron spectrum of helium, that would be nice. Go ahead. By the way, in your exam, you might have to draw fourth electron spectra. Okay, there were past questions asking you to draw photoelectron spectra, so it's not a bad idea to get used to drawing them. And by the end of today, you should be able to draw photoelectron spectra for any element in the periodic table. Your name is? You email me. Did you see your oral grade? Yeah. Yeah, yeah. Yeah, they update it automatic. Huh? Yeah, wonderful. Everybody should draw it, okay? I mean, I just want to get you to think about this. Now, get in there. Good start, okay? A good start would be, drawing the axis and labeling them. Or whenever we draw something, draw a graph especially, label them. We need a marker pen. Oh, yes. If we have more marker pens, can we have them here? I mean, some of these are not writing. Can we get rid of that? Yeah, thank you. Yeah, can you go to the front desk and ask for marker pens? Thank you so much. All right, so, all right, I think I've seen a couple of them at least. All right. Sophia, can I see yours? What did you expect? Thinking about, okay, okay. All right, wonderful. All right, so if somebody asked me to draw the photoelectron spectrum of helium, I would draw something like this. Here we go. Okay, it has two electrons rather than one. Therefore, the peak height will be twice as that of hydrogen. And also, because helium has more protons in its nucleus, the ionization energy will be higher as well. So here goes nothing. Here we go. All right. So this is what we would expect for helium. Okay. Now, just to compare this with hydrogen, and okay, hydrogen, there's only one peak is lower compared to that of helium, and also you can see that the ionization energy has increased for helium. Why? You have more protons in the nucleus. More protons means electrons are more strongly attracted to the nucleus. As a result of that, it's harder to remove them. Okay, that's why we have a peak like that. All right. What questions, concerns, comments do we have? All right. So can we draw the photoelectron spectrum of lithium? And also there are two shells. So in the first shell, you have two electrons filled. And then in the second shell, you only have one electron. And we know because the two shells are separated, okay, if there's energy gap between the two shells, you should have two peaks there. Okay. So as a result of that, the lithium photoelectron spectrum will look like this. Okay. Now, one of the questions that you had to ask yourself, okay, was the peak with two electrons, should it have a higher ionization energy or lower ionization energy? It should have a higher ionization energy. The reason is the one with two electrons are closer to the nucleus. As a result of that, they're going to feel the positive charge of the nucleus more. Therefore, those electrons are more strongly attracted to it. Therefore, higher ionization energy. Okay? So the first shell is closer to the nucleus. As a result of that, ionization energy of those electrons will be higher than the outer shells. Yeah? All right. What questions, concerns, comments do we have? All right. So if that is the case, I'm going to do one other thing. All right. So here's beryllium. All right. We have four electrons. Okay. But two of them are in the first shell and the other two are in the second shell. So it's going to look like that. All right. Here's a test for you. can you draw the photoelectron spectrum of boron? Go ahead. Boron on your whiteboards. Okay, for boron, I have, okay, that, yeah, okay, okay, okay. So based on what I know now, as of now, thank you. Thank you. Okay. Based on what I know now, if somebody twisted my arm and asked me to draw the photoelectron spectrum of boron, okay, according to the shell model, I would draw something like this. So boron has how many electrons again? 5 electrons. Okay, it has 5 electrons. Okay. So the first two will be filled to the first shell. Okay, so 2 electrons in the first shell. And then in the second shell, you have 3 electrons. Okay, so I would draw something like this. Boron. That's it. Okay, according to the shell model, we have 2 shells in boron. Okay, so we have 2 in the first shell and 3 in the second shell. Okay, and the ionization energy, remember, should be higher for the one closest to the nucleus. That's why you have a higher ionization energy for the one with 2 and lower one for the one with 3. I'm going to come back. Give me a second, okay? All right. All right. What questions, concerns, comments do we have? All right. What questions, concerns, comments do we have at this moment? I know William's group have some questions. William, what's your name? Is almost. I'm sorry. Kira, you have a question, right? Yeah. Can I have the microphone there, please? All right. Now pay attention for a second, okay? Go ahead.
How do you know how many electrons each shell can hold?
Oh, how many electrons? The maximum number of electrons in a shell? The first shell is 2, the second shell is 8, and the third shell is 8 as well, and so forth.
So all of the shells after the first one are 8?
Come again?
All of the shells after the first one?
No. I mean, it differs after that a little bit. I mean, we'll talk about that in a minute. Yeah. So I saw that some of you have a different photoelectron spectrum. Yes. I'm sorry. I forgot your name one more time. What remember your name is one more time?
It's Delaney.
Delaney, go ahead.
We're just like really confused how you're getting like any of this.
Can you repeat one more time?
We're just like confused how you're getting any of this. Like if I look up the shell model, I get that, but I don't know how we knew that without looking up
Yeah.
on
So
Google.
that's okay. So how did I get this? I want to go to the next stage really quickly. Okay. Delaney, keep the microphone. That's the reason. No, keep the microphone. Keep the microphone with you. Okay. So Delaney, how many electrons does boron have?
5.
5. How many shells does it have?
How do we know how many shells it
Because
has?
the row. What row?
Okay, row.
How many rows do we have in boron? 2, right? So it's in the second period, meaning it's in the second. Okay, it has 2 shells.
Yes.
Yes. The first shell can only have 2 electrons. The other 3 must go to the third the second shell. That's it.
Okay, now that makes sense.
Kim, is that right?
Yeah.
Yeah, Kim, go ahead.
Is the second shell like the third row?
Second row.
Okay.
First shell is the first row is the first shell. Second row, second shell. Third row, third shell, and so forth.
Okay, so but like it has
Can you
5 in
please pay
total.
attention? TS, can you walk around to the people who are chatting so that you can help them? Yes.
Okay, so it has 5 in total. So 2 would be on that row, the row of the boron, and then the rest of them would be on the
The second
third.
shell.
Okay.
Yes.
Does it matter how many more it has?
No, it has only 5.
Oh, but like if it were to have more, would it be like going
Yeah,
down?
we'll do some more.
Okay. Thank you.
All right. All right. Now, I didn't get the real question yet, actually. William, do you have a question about this? William, do you have a question about this? No. Do you have a question about this? Are you okay with this? Here's the thing, though. All right. Can you pay attention? All right. We are gonna scratch this out in a second. So I want you to pay attention, okay? So This is what we should expect based on the shell model, right? However, when we actually do the experiment for boron, we get this. This is the actual photoelectron spectrum of boron. Okay. So what's going on here? Anybody? William, I thought that you had this in your as your answer, but nobody asked me about this. Anybody knows what's going on here? All right, you know what? I'll tell you what's going on. Shell model fails. That's what is happening here. Okay. In science, this happens, more often than you think. Okay. The models we come up with fails. So what do we do when that happens? Anybody? When one model fails, what do we do? Thank you. Okay. We are going to try another one. We're going to modify our model and then, use a modified shell model. By the way, the actual model is called modified shell model to explain this. All right. So according to the modified shell model, the shells have subshells. Okay. So here's how it goes. I'm going to show you this. Right. According to the modified shell model, the first shell has only one subshell that is called 1s. Okay. It has a capacity of 2 electrons. And the second shell has 2 subshells. You have a question, sir? TS, can you go there and see if they have a question? Do you have a question? Yes? Okay. TS, if they have, okay. If you can go to them and help them out, that would be wonderful. All right. So second shell has 2 subshells. Okay. They are called S and P. Okay. S again still have only 2 electrons. They can only accommodate 2 electrons. And P can have up to 6 electrons. And the third shell has 3 subshells. They are called S, P, and D. Let me ask you a question. Fourth shell. How many subshells do you expect in the fourth shell? Thank you. 4. What do we call them? S, P, D, and F. Thank you. Maybe you have heard of them before, right? Okay. So with that, let's do this. I'm going to actually, draw the correct photoelectron spectrum for a boron. By the way, this is wrong. Why? This is not what we see experimentally. Experimentally, we see ionization energy increases this way, number of electrons. Okay. We see 2 electrons, and then we see 2 electrons, and then 1 electron. Okay. That's what we say. So where do we have them? We have 2 electrons in 1s subshell, and then we have 2 electrons in 2s subshell, and then we have 2 electrons in 2p subshell. Right? So if you write this out, boron has 1s2, 2s2, 2p1. What did I just write here? Anybody knows what we call this? This is known as the, William, do you know? No, but what is this entire thing? I just wrote what of boron? Thank you, the electron configuration of boron. Okay? And this is coming from photoelectron spectroscopy. All right. What questions, concerns, comments do we have at this moment? Let's do another one. Fluorine. Can you draw the photoelectron spectrum of fluorine and write the electron configuration? Go ahead. Draw the photoelectron spectrum of fluorine. And you might want to pay attention to the capacity. Okay. S can only have 2, P can have 6, and D can have 10, and F can have 14. So those are the capacities of the shells, subshells. Otherwise, you're going to learn that the hard way in your lab, okay? So, and the other thing is, we're looking at fluorine. How many electrons does fluorine have? Thank you. 9 electrons, right? Fluorine has 9 electrons because the atomic number of fluorine is 9. Here's what we need to do. So we know we have subshells, right? We start with 1s, that's the closest to the nucleus, then 2s and 2p from the second shell, and then 3s, 3p, and 3d from the third shell, and so forth. Okay. Now, what we want to do is, I have 9 electrons. I want to distribute these 9 electrons among these subshells. I know S can only have up to 2, therefore I'm gonna have 2 for S, and same thing for 2s, only 2 for 2s, and P can have up to 6, therefore I cannot have 6 here because I only have 9, so I'm gonna only have 5 for P. Okay, and I don't need the rest. So the electron configuration of fluorine should look like this: 1 is 2, 2 is 2, 2p5, and then I'm going to draw the 4 electron spectrum. 1 is 2 is the closest to the nucleus with the highest ionization energy. Okay, it should be 1 is 2, and then in the second shell I have 2 is 2 and 2p5. Done. That's it. All right. What questions, concerns, comments do we have at this moment? Anything? Yeah, Kim, go ahead.
Okay. So on the graph, as it's going to the left,
Raise the microphone. Yeah.
sorry. As it's going to the left, it's increasing. So is the IS bigger than like the less electrons it has, it's the bigger?
So the ionization energy, right? You're referring to ionization energy, is that right?
Yeah.
Yeah. So ionization energy will be higher as you move closer to the nucleus.
Okay.
First shell is the closest to the nucleus. That is going to have
Oh, it
the
has
highest
more.
ionization energy.
Okay, so that's why it's going this way, not
Yes.
like the other. Okay.
Yes.
Okay, thank you.
Delaney, did you have a question? All right, can you please pay attention? TAs, can you walk to the tables who are chatting and then ask them whether they have questions, please? All right, Delaney, go ahead.
Can you like explain this one again? I'm so sorry. It's just like not making sense. Like the
Okay, so
Yes,
Delaney,
it's in the
how many
piece.
electrons does fluorine have?
9.
9.
Yes.
Okay, and 1s can have only 2. Yes,
Yes.
this is an S orbit, S subshell, and 2s can have only 2 as well. Yes,
Yes.
and P can have up to 6, but we need only 5 to be filled there. That's it.
Perfect. Got it. Thank you.
Very good. So all the whiteboards I've seen so far are absolutely correct, which is wonderful. All right, this wasn't the case at the beginning, but I think we're getting there. All right, let's do this together, everybody. Delaney, are we doing okay? Delaney? Yes, wonderful. Okay, so here's the question for you. How many electrons does phosphorus have? How many? 15. Thank you. Is it 15? Yeah, perfect. Okay. All right. So what we want to do is we want to distribute those 15 electrons in subshells. Okay. We know first the first shell will be filled. First one is subshell will be filled. Then 2s, then 2p, then 3s, then 3p, then 3d, and so forth. Right? Okay. 1s can only have up to 2. S can only have up to 2. Any S subshell can only have up to 2. Okay, so I'm going to have 2 there. Then the 2 again for the 2S subshell. And then P can have up to 6. So I can have 6 here. Now I have 10 electrons. And S3S can only have 2. And then I have now 10, 12 electrons. 3 more electrons left. Therefore, 3P can have 6, but it has only 3. So this is all we need. So 3D is not needed. Therefore, the electron configuration of phosphorus is this. Okay. Now we draw the 4 electron spectrum. 1s is the closest to the nucleus with the highest ionization energy. Okay. This is 1 is 2. And then I'm going to separate my first shell from the second shell with a large energy gap. Here's my second shell. 2s of second shell has 2 electrons. And then we have 6 electrons in 2p. And then I'm going to separate my third shell from the second shell with a large energy gap again. Here's my 3s2. And then in 3p, we have 3 electrons. Therefore, I'm going to draw them over here. Another Christmas tree. with 3 electrons. There you go. So this should be the 4 electron spectrum of phosphorus. Done. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? All right. Now, we should be able to draw 4 electron spectrum of any element in the periodic table. Okay, this is all we do. Now let's have some fun with this. Oh, by the way, before we have some fun with this, I'm gonna use 2 more minutes to tell you something. Then I want you to forget about that, okay? All right, here's how it goes. So it turns out the modified shell model is not the most accurate model either. Okay, so the most accurate model is called the quantum mechanical model. And according to that, get this, subshells further splits into sub-subshells. I did not make this up. It is on my slide. Look at this. Okay, we have sub-subshells. For example, the P subshell has three sub-subshells called PX, PY, and PZ, and how they are based on how they are situated in the space. Okay, and the D subshell have 5 subshells. I'm sorry, D subshells have 5 sub-subshells called dxy, dxz, dyz, dx squared minus y squared, and dz squared. All right. So, and then so these sub-subshells are also known as, anybody? Does anybody know what we call these sub-subshells now? You might have heard about this in high school or somewhere, but you don't have to know this. But they are known as orbitals. Okay, these are known as orbitals. Okay, and here's the thing. Orbital is a region of space where the electron can reside. And get this, there are only 2 electrons can simultaneously occupy an orbital. There's only 2. And this is due to a principle called Pauli exclusion principle. Okay, so reason is electrons are fermions. Okay, fermions have what we call spin values, intrinsic spins. Okay, you can only have like like spin up and spin down there. But if you try to include the 3rd electron, that electron will have a spin up or spin down, which is not going to be allowed in the region of space. Okay, for that so this is the same reason why neutron stars do not collapse. Okay, so neutrons have the same issue. They have spins. All right, so they need to be have only like unique quantum numbers. If you don't have them, they're going to collapse. All right, anyway, that's it. Forget about those 2 slides. All right, I just want to mention that for the completion of our discussion here. All right, I think we have more than 90% answers. I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our results. That's beautiful. Oh, look at that. All right. And that's the correct answer as well, 95%. All right. So this is a good stage to introduce something new. A little something new. It's not that, radically new. Okay. So when it comes to chemistry happens with the outermost electrons. Okay. So now, if you look at this, you have 3 shells here. The outermost shell is this shell over here. And then this shell over here is the inner shell. Okay. And the entire thing is called the core shell. This is called the core shell. Okay. So core shell almost always have a noble gas configuration. Okay, for an example, so you will see that in this case we have 1s2, 2s2, and 2p6. All right. What is this configuration? This configuration belongs to what noble gas? Anybody? Can you check? This configuration belongs to what noble gas? I hear that lightly. Thank you. Neon. Right? So So this element has the neon core shell, and then this outermost shell is called, does anybody know the name of that? William? Thank you. This is called the valence shell. Valence shell. Valence shell. Okay. And that's what participate in chemistry, by the way. Okay. And the valence shell has 3s2, 3p4 configuration. Okay. So when we write the electron configuration, I believe this is 16, it should be sulfur, right? Sulfur. Okay. When you write the electron configuration, you can either write this, or you can write the electron configuration of sulfur as neon core shell and 3s2, 3p4. This is called the noble gas notation for the electron configuration. In 5, 4, 3, 2, and 1. All right. And here are our responses. Okay. There are 6 electrons in the valence shell. That is true. The third shell is the valence shell or the outermost shell. You have 4 plus 2, 6 electrons. Okay. And then there are 10 electrons in the core shell. That is true. 1s2, 2s2, 2p6 has 10 electrons. Okay. And then the atomic number of the atom is 16. That is true as well. All right. Any questions, concerns, comments about this? What questions, concerns, comments do we have? Anything? All right. So I think we are good with electron configurations, 4 electron spectra, and the idea of core and valence shells. Now, let's do this. Let's write electron configuration of germanium. Let's do the noble gas notation. Here we go. Let's see. All right, I'm going to leave this open. I have more than 90% now, I think. At least close to 90%. Very close. Okay, so now, yeah, if you can pay attention for a minute, I'm going to show you how I would tackle this. There's one little thing that we, like strange thing that we need to get used to, but we will, okay? Here's how it goes. Please pay attention now, okay? TAs, please pay attention as well, okay? So, go to the tables, if they're still talking, and help them orient and focus. Okay, so here's what we need to do. We need germanium. Here's okay, I need a better pen. All right, germanium is over here. Okay, to get to germanium, we need to fill up to 1, 2, 3, the third shell. That means germanium should have the argon core shell for sure. Okay, so I can write germanium, right, has argon noble gas core shell. Okay, and then in the fourth shell, where the germanium is in, we have the S subshells completely filled. Therefore, I'm going to write 4s2. And then I have these guys filled. These are D, but get this, these are not 4D, these are 3D. Okay, we have 3D subshell completely filled. We have 10 electrons in the 3D subshell. And then in 4p, I have only 2 electrons. Therefore, I'm going to write 4p2. Okay, so if you wrote the electron configuration of germanium like this, you will get credit, at this stage. But if you want to be technically more correct, I would rewrite this saying, okay, I would rewrite the electron configuration to look like this. We have argon core shell, okay, and then I'm going to switch 3d10 over here. And then in the core shell, we have 4s2. I'm sorry, in the valence shell, I have 4s2 and 4p2. Now, why do I call this my valence shell? You see that number 4 is higher than number 3. Okay, so that number indicates the number of the shell. Higher the number, okay, outermost that shell is. So fourth shell is the outermost shell, and therefore this should be my valence shell. In the valence shell, I have 4 electrons in germanium. All right, I'll give you 30 seconds to think about this, and then I'll take any questions you might have. Go ahead.
I don't know if it's over. But I can make a gas question. So the chart thing, sorry. Okay, yeah. So the graph that Olivier has is really good. Yeah, see, like they go up to that. Like, so if you like, that's just online. So if you look at like subshell,
All right.
like subshell energy.
All right. What questions, concerns, comments do we have at this moment? What questions do we have? Please, if you have any, this is your time to ask. Kim, thank you. Can I have the microphone with Kim, please? All right. Now, please pay attention. Chances are you have the same question as well. So let's see. Kim, go ahead.
So I had put the AR, but then I added like the 1S and I built it up that way. So why would that be wrong if
Give
it
me a
still
second.
adds up?
You had AR, okay, argon core shell.
Yeah.
After that, you had
I-
4S.
I had 1S
Yeah,
and then
give
I
me a
went
second.
up that
So when
way.
you have AR, okay, or argon,
Yeah.
argon already has 1s2, 2s2,
Oh,
2p6, 3s2, 3p6. That's already there. You don't rewrite that.
So you can only add it up with like the 3 and the
You
4.
write the rest. Okay, you write up to argon is with the square bracket, and you write the rest. In the fourth shell, we have 4s2 and 3d10 and 4p2. That's what you write.
Okay, so if it was like a bigger value as well, you would keep going like to 5S.
Yeah, beyond that, beyond
Okay,
the
and they
quotient.
have the same values as the initial ones, right? Like as the 1S, it's the same value.
You mean value means the number of electrons they can have? Yeah, they're the
okay.
same. S is 2, P is 6, D is 10, and F is 14. That's
Okay,
right.
that makes sense. Okay, thank you.
Yeah. All right. What other questions, concerns, comments do we have?
There's one question here.
Yes. Perfect. What's your name, Miss?
Alexis.
Alexis, go ahead.
So for the like the electron
Can you please pay
spectrograph,
attention for a second?
for the spectrograph, would the 3D10 be to the left? Would it be the core? Like when you're graphing it?
No. 3D10, yeah, I'm sorry. Yeah, you are right. 3D10 is considered as a core shell, part of the core shell.
And then
Again, the reason is, remember, 4 is higher than 3. Therefore, fourth shell
Oh.
is the outermost shell, and that is the valence shell. The others are core shell.
and on the test, would we get marked off if we wrote it like the first
The top
way?
one,
Yeah, the top one.
I want to say no. Yeah, let's go with no.
Okay.
Okay, but technically it's more correct to write the second one. Yeah. All right. Any other questions from this side? I got 2 questions from this side. Anything from this side? Any questions, concerns, comments? Everything okay, sir? Yeah. Yeah. Okay. Okay. Anything? Thank you, Jack. Right? Yeah. Can I have the microphone with Jack, please? Jack, go ahead.
We were going to ask if we could have an example of something greater than Krypton because we're not sure how we'd go about
Something greater than.
Krypton.
Oh. I do not have it here, but actually we can try it. So Jack, can we so no, I'll okay, let me see. And so I mean, do we have examples? Of course. Okay. I mean, if you go to the periodic table, for an example, if you write the electron configuration of say iodine over here. All right, let's write it here. Okay. I mean, I'm gonna do it for the sake of time. All right. So to get to iodine, we need to fill up to krypton. Okay, so iodine will have krypton core shell. Oh, that's where Superman was, right? Okay, anyway, and then after that, this is 1, 2, 3, 4. We are in the fifth shell. So we have 5s2. Okay, and then we have completely filled 4d, 4d10. And then in the 5p, we have 1, 2, 3, 4, 5 electrons. Therefore, I'm going to write 5p5. So if I rewrite this for iodine, I'm going to have krypton core shell. And then I'm going to add 4d10 to that. This is going to be inert now. And then in the outermost shell or the valence shell, we have 5s2 and 5p5. Is that what you're asking, Jack? Yeah.
Yeah.
It's the same thing over and over. Huh?
It just
Yeah.
continues on.
Yes. Yes. All right. I'm gonna come to you in a second, okay? So I'm gonna talk about something. Give me a second. I'm gonna go in a minute, Alexis, in a minute. So just to complete our notes here, okay? Can we try this? So here's a table for you. What I want you to do is so I already wrote the electron configurations for you over here. I want you to write the number of vacancies in the valence shell. Okay, here's how we do it. So for example, let's take nitrogen. Nitrogen valence shell is the second shell. We have 5 electrons now, but it can have up to 8. Okay, because we only have 5, you have 3 vacancies in the nitrogen valence shell. Okay, and then you write the common bonding capacity of nitrogen as well. Oxygen, we have 6 electrons now. We can have up to 8. Therefore, how many vacancies? I heard that too. Thank you. And then guess what? The common bonding pattern of oxygen is also 2. Okay. Fluorine, we have 7 electrons. Okay. Now, okay, but it can have up to 8. Therefore, it should have 1 vacancy. And the common bonding pattern is also 1. Can you fill out the rest, please? And I'm going to go talk to Alex. Common bonding pattern of carbon is 4, nitrogen is 3, oxygen is 2, fluorine 1, phosphorus is 3, sulfur is 2, and chlorine is 1. How do we know it? If you go to the periodic table, okay, one more time. We just need a reminder for that, okay? So this column over here forms 0 bonds. This column 1 bond, 2 bonds, 3 bonds, 4 bonds, and that's how we know the common bonding pattern. Now, our task was to explain that, okay? Now, to do that, we wrote the electron configuration and the number of vacancies in the valence shell. For phosphorus, we have 3 because you have 5 electrons now. We can have up to 8, therefore 3 vacancies. Same thing with sulfur. We have 6 electrons. We can have up to 8, therefore 2 vacancies. Chlorine, we have 7 electrons. We can have up to 8. We have 1 vacancy. Okay. So what do you notice? The relationship between the number of vacancies and the common bonding pattern. Thank you. They are the same. So that is how we explain the common bonding patterns of the elements. Okay. The elements form a number of bonds that is equivalent to the number of vacancies they have in the valence shell. All right. What questions, concerns, comments do we have? So there were past exams like free response questions. All right. You had to justify the common bonding pattern of element by writing out the electron configuration and determining the number of vacancies in the valence shell, and then saying that the number of vacancies in the valence shell is equal to the common bonding pattern of the element. That's it for the full credit of that question. Okay. So, I'm telling you the answer for one of the free response questions. Previous one. I don't know whether it's going to be there this time though. All right. Now with that, we know all that. Let's do this. We have X atom and we have Y atom. Okay. 2 hypothetical atoms with these electron configurations. You are only shown the valence shell electron configuration, because that's what matters to the chemist, which okay. So before I look at your answers, I'll leave this open. And no, I want to close this. I want to see your thinking. Okay. So here's what we have. All right. Actually, give me a second. Okay. So in X, the valence shell has 4 electrons. We can have up to 8. We only have 4. Therefore, this has 4 vacancies. Okay, 4. I don't want to write vacancies. Oh my goodness. Okay, I'll try though. 4 vacancies. Okay. So therefore, X is going to form 4 bonds usually. Common bonding pattern of X is 4. On the other hand, Y has 6 electrons, can have up to 8. Therefore, it has 2 vacancies. Okay. So therefore, Y is commonly going to form 2 bonds. Okay. And then, X is like carbon and Y is like oxygen, if you want to compare to something that you're familiar with. But anyway, so if you combine them, we can have X in the middle. And if you bond them twice to a Y like this, and another one twice like another Y like this, okay, this will give us the structure of this compound, and it has a formula of XY2. Done. That's it. So here's what we're going to do next. All right. When we come back on Tuesday. Oh, before we do that, we need the attendance code. Oh. The attendance code for today is this. When we come back on next Tuesday, we will draw Lewis structures and we will talk about the idea of resonance.